In this lecture, we will take a look at a method for finding a polynomial that passes through a given set of points. We are given a total of n plus 1 points, starting with x sub 0, y sub 0, all the way up through x sub n, y sub n. We will be searching for a polynomial function, that is, y will be a function of x. For this, we require that the x-coordinates be distinct. That is, x sub I is not equal to x sub j if I is not equal to j. The polynomial function that we will find is what we call a Lagrange polynomial. It is the polynomial of smallest degree that passes through all the points. It is a well-known fact that there is a unique polynomial of smallest degree that will pass through a set of points such as the set that we are given. The truth is that for n plus 1 points, the degree will be no greater than n. Let the polynomial that we are looking for be f of x, which is equal to a sub 0 plus a sub 1 times x plus a sub 2 times x squared, all the way up to a sub n times x to the nth power. Finding this Lagrange polynomial means that we have to find a sub 0, a sub 1, all the way through a sub n. In short, the a sub i's are the unknowns in the problem. And so, we need to find a set of equations for these unknowns. We get this system of equations by simply plugging in the coordinates of each of the points into our function. Starting with x sub 0, y sub 0, f of x sub 0 equal to y sub 0 gives us this equation, followed by x sub 1, y sub 1, and so on for the rest of the other points. Let us write the system in matrix form. We write out the left side of the system of equations as a coefficient matrix capital A multiplied to the vector of unknowns. On the right side, we have the vector of y-coordinates. To write out the rows of capital A, we take a look at each equation and obtain the coefficients of the different a sub i's. From the first equation, we have 1, x sub 0 to the first power, x sub 0 squared, all the way through x sub 0 to the nth power. And so we have the first row of the coefficient matrix. Do the same for the second equation, and get the second row of the matrix, and so on for the other rows. This matrix is a very well-known matrix. It is called the Vandermonde matrix. As long as the xi's are all distinct, the inverse of this matrix exists. And so all we have to do is multiply this matrix equation by the inverse of the Vandermonde matrix, and we will have our vector of unknowns. And this will be equal to the inverse of the Vandermonde matrix multiplied to the vector of y values.